All right, so let's continue from the first 3D assignment. So we ended basically with this lab exercise 3 here, right? And basically had objects moving around in 3D space just a little. We could transform, we could push and pop the matrices, work a little bit with the model matrix, work with the color of objects. But we haven't started moving ourselves around at all. So I'm going to look at lab exercise 4 here, which starts with a few pointers of it or advice, basically similar to the others, this efficiency optimization that I took at the end of the video before, as well as these ideas on how to make sure that the relative paths are correct. And then it basically dives into the idea of setting up more matrices to use in the vertex shader. So let's just start there and see if we can little by little make things work here. So right now in our vertex shader, we have something that's called the projection view matrix. And what we're sending in there is simply a hard-coded matrix. Go here into matrices. I have this class projection view matrix, projection view matrix, and it simply returns this hard-coded matrix, which I just calculated from some values for a combined perspective projection matrix and a view matrix. So let's go through this in steps in order to be able to kind of see something happening the whole time. To begin with, let's see what everything looked like before. Python. Yeah, it was probably this huge cube of, okay, cool. Let's lose some of that. Make everything a little bit simpler. Let's just put these original cubes in here again. Uncomment that. Comment all of this out instead. So, see what this looks like. Just to have something that we're starting from. Not sure what happened there. Okay, is there something that I'm skipping that? Aha, okay. This optimization here, we said we don't need to set the vertices every single time we draw. That still means that we have to set them sometime. So if I'm going to be drawing cubes now, might as well do this. If cubes is the only thing we're drawing in our program, we might as well just have this function here in our init function or wherever. But let's imagine that we're switching between models every once in a while. So here we have these different shapes, these differently scaled and translated cubes. So let's go into the vertex shader and say we don't want to have this projection view matrix here. We want to have a view matrix and we want to have a projection matrix. Inside our shader, we can actually just go ahead and say, well, the only thing that changes in a simple shader like this, since we're not doing anything special between doing the view transformation and the on the projection transformation, we might as well just, no, sorry, it would be like this. So first we multiply the view matrix with position, then we take the result from that and multiply that with the projection matrix. So if we want it to be super clear, we can put these parentheses, but it doesn't matter. If we want to be even more clear, we can also go ahead and just say we're going to start by multiplying position with the view matrix, then we're going to multiply position with the projection matrix. So this is very explicit here. We are first doing the view transformation, which leaves us in I coordinates. And then we do the projection, which leaves us in clip coordinates, which are the coordinates that we actually want to send to GL position, because that is the type of coordinates that OpenGL understands for the next operation in OpenGL in the pipeline, which is clipping. All right, so from local to global to I coordinates to clip coordinates using these matrices. Now, however, we need to go into our shader, and we need to say we don't have a projection view matrix location anymore. We have a view matrix location, one variable for that, and another variable for projection matrix. So let's say we have the view matrix location here, projection matrix location here. All right, so we basically just copied that and made one for each. Do the same for the functions where we set the values. Just view matrix, just view matrix, just the projection matrix, just the projection matrix. Otherwise the same. So we just have more functions to send these things in. Now we need to look at the matrices. So we have this orthographic projection here, and it's okay to look at that to begin with. And then we have the view matrix, which basically sets up this base here. I'm simply going to remove the projection view matrix entirely. It has no purpose really. And then we also get errors if I'm trying to use it someplace. So now we're going to say, we can actually, to begin with, just say we're going to make a view matrix here. We are going to set the view matrix. We are going to make a projection matrix here. But we actually need to set some values for that. This is the projection matrix. So a bunch of copying and pasting here. Okay, so the projection matrix. Now let's see if this at least compiles and fix any errors that come up. It's probably not going to show anything because we've completely changed from this hard-coded matrix that we originally had. What I want to do to begin with is to set something in the projection matrix here. So let's say set self projection matrix, set orthographic, and I think something like, so an orthographic projection is simply a projection without any perspective. Stuff that is far away is exactly as big on the screen as stuff that is close by. It's like just taking a box that's parallel with the axes of the coordinate system and just projecting through that. So we're not actually projecting towards a single point that is the eye of the camera, we're kind of projecting towards a screen through a tunnel that's exactly as wide as the screen the whole way. Just have this near plane fairly close and this far plane, something like this. Okay, so I'm setting up an orthographic projection. Setting up, again, we'll probably see nothing, just make sure everything. Okay, we do see something. So some of this is actually seen through here, since we had moved it around a little bit. So what I'd like to do is to take that purple box. Everything just looks flat 2D now. Take that purple box and do some rotations on that. which one was the purple one? Here. So after we translate, but before we scale, let's do self model matrix dot add rotation around X, angle, you can just make it fairly slow, like so, and let's also add a rotation around Y. That's even slower. Okay, let's see. Angle, no, that would be self angle. Like so. I just want to see that it rotates, see that the lighting is correct, see that it's actual 3D. Okay, so it is 3D, but just looking at it, it looks super strange. It looks like it's kind of undulating in shape as well, because we're used to seeing things in perspective, where things that are further away are smaller than things that are close. So this looks extremely weird, but at least we have things moving around and we have some control over our camera. So let's leave that for now and just build the perspective projection later on. So now we have some projection, so we'll leave the projection for now and just look at the view matrix. Let's go back into matrices. Look at the view matrix, which basically already here we have, it sets up the I, U, V, and N, which is the coordinate frame of the camera, the local coordinate frame of our camera. And it also builds the matrix. So this matrix that has the U vector here in the first row, V vector, N vector, and then these dot products, which is basically inverse of how we build the model matrix usually. And we already have this. So GetMatrix simply takes whatever I, U, V, and N values we have at this current point. It calls, it builds this array here with these values, and then it returns that array. So what we can do in our program here when we want to set this view matrix is we call ViewMatrix GetMatrix, and we send that into the shader. In the shader, it'll say, okay, I have a variable that is handled by this view matrix location. I want to send that into the shader. View matrix location is a handle here to the U underscore view matrix in the vertex shader. Here we have that variable. It'll get those values and it'll use them when we multiply the position with it to get the position in I coordinates. So again, link the whole chain. So we have this whole chain. The only thing we need to do is actually get values into I, U, V, and N. Right now it's just an identity matrix, which means it's like the camera is sitting in 0, 0, 0 and just looking directly along the negative z-axis. So anything we want to be seen in front of it needs to be somewhere in the negative z area. But it'd be nicer just to be able to move the camera to wherever we want and look at whatever we want. So first operation we'd like to build is look. And this operation needs to take some point that tells us where the camera should be. It should take some point that tells us what the camera should be looking at, and then a vector that's called up. So we have here in basic 3D objects, we have point and vector, we have length, normalize, we have dot product, we have cross product, we have adding and subtracting and multiplying with scalars, all kinds of things on the vector class. So we should be able to simply, what was it, matrices? To simply say we have a formula for how we can take these and set up the camera's coordinate frame. So self I will simply be I. That's the point of origin in this coordinate frame. It's just unchanged. It's where we're supposed to be at. Then we can say self.n equals, that should be directly backwards from us. So that would be I minus center, the vector from center to I, which is the vector towards us, which is then backwards from us. So I is a point, center is a point. The way the subtract on point is defined is that it returns a vector. So that vector would have a function called normalize. So we should be able to go in here and say this vector that is returned dot normalize is n. Now we can say self.u equals the vector up that was sent in here, cross product of that and the vector n, and then we can normalize that as well. And finally self.v equals n cross u. It matters in which order we do this. U cross n isn't exactly the same as n cross u. Yes, true. Self.n and also self.u here. Okay, so we have some value for the I, we have a value for n, we have a value for u. We've normalized both of those. Why is this complaining? Self.n, we do the cross product of n and u, which are both normalized and also perpendicular to each other, which means that we know that the cross product of those will also be unit length. So we don't need to normalize the vector v explicitly. So is this everything we need? Now we have values for I, u, v, and n. So the next time GetMatrix is called, we should be able to, or we have all the values that we need. So to begin with, make sure it compiles. Then let's see how we can use this. Okay, so we're still at the same location looking at the same stuff. Now we would like to go into the program itself. Say instead of ViewMatrix just setting the ViewMatrix, let's call look. Now very soon we'd like to be able to move the camera around, and then we can't set the ViewMatrix just in this initializing function here. We have to actually do it in the display function because we'll have new values for it every frame, which means we have to actually set the new values for the ViewMatrix every single frame. But for now, self.ViewMatrix, sorry, dot look, point, let's just say we want to be in 333. We want to look at the point 0, 0, 0, and up should be 0, 1, 0. Let's just try that now. See if we at least get some change. Okay, that was a change. It is telling me I'm trying to do something with a none type. So where does that come from? Object has no attribute z. Can anyone see what's bothering this here? So in matrices, calling the cross product, in base objects, it's doing the cross product. I know the cross product is correct, so for whatever reason, something of the stuff that's sent in here is not correct. Non-type object has no attribute z. Why?
I minus center normalized doesn't return anything.
Okay, let's see it. So I minus center should have returned a vector. Ah, okay, sorry. I was thinking, okay, normalize doesn't work like that. Sorry, normalize doesn't return. New one normalize normalizes the vector. That was me forgetting exactly how I implemented this. Cool. These can be implemented in both ways, and actually in the shading language inside the shader, if you call normalize, it returns a vector that's the normalized version of what you called it for. But then you actually call normalize of the vector rather than the vector dot normalize. Here, however, we can fix this. I go into matrices here, and we will simply say n equals I minus center, and then we just do self n dot normalize. This is just an implementation detail. Yep, self dot n dot normalize, obviously. And then we do the same thing here. Self u is up n, self dot u dot normalize. All right, let's see if this works better. Okay, so I'm seeing the same scene, but I'm seeing it from someplace else. It wouldn't change anything if I move further backwards or forwards when I'm using this particular projection. So let's at least see if we can go into matrices here. So now we have look. We can tell OpenGL that we want to be someplace and we want to look at someplace. Now let's define slide. Ceph define slide, which would basically take how far we're going to go along the u vector, how far we're going to go along the v vector, and how far we're going to go along the n vector. So these are relative movements to the camera. Self.I equals self.u times delta u plus, and so on and so forth. Since we have the plus and the multiplication implemented on vectors and points, we can just do this in one line. Self.n times delta n. Okay, so now it would be nice to be able to go in here. You can add some keyboard possibilities here. Say W for forward, S for backward, A and D. Oh yeah, then we have to make all these keys as well. W key down. So make them all false as well. In this case, yeah, we have to make these variables as well. Sorry about the fast scrolling, it's just best not to waste too much time on all this. That was W, S, A, D, and then we should be able to go here into update and go and say, so if W key down, we are going to do self dot ViewMatrix dot slide that would be 0, 0, and something like -1 times delta time. 2, 3, 4. So then we have W, we have S to go backwards along the positive z-axis. We have A to go along the negative x-axis. The reason I have -1 times it rather than just delta time is because I'm probably going to want to change this to make it faster. D, and since we're changing this, then we now have to go ahead and say I can set the matrix up here and I can make the look, but I'd like to take shader.setViewMatrix, and I'd like to do that every single frame. So in display, after I've basically done this, cleared it, I'm going to set the view matrix here every single frame, so we get a new view matrix. Let's see if this has any effect here. Okay. Why did the slide kind of jump there and then not work? A key down, and did I do anything wrong in the keys, or is it the slide itself that's acting weird? One thing we could do, we could just take this out here and just fix a slide here. Just slide along the This feels weird. Set the view matrix here as well. I wonder if there are copy-paste errors someplace else.
Go to matrices.
Yeah?
Self.I plus equals.
True. Self.I plus equals. Sorry. Not just equals. We have to actually add this to it. Thank you. So let's see what happens if we run this now. Now I should just get a slide. Okay, we're just sliding down here. Now let's take that particular slide out. Put the other ones in instead. So now I can move to the side here, and I can move forward and backwards. I'm moving forwards now. I'm moving backwards now. So as I'm moving backwards, nothing is happening until probably I get so far away that I'm more than 10 away. Saw that disappear. So this is just the far plane clipping. But since this is an orthographic projection, you know, nothing is getting bigger or smaller as I move forward and backwards. So I can move to the sides, but the other motion just doesn't make any sense. So I think that would be a nice time to try to get something happening in the projection matrix, to get a perspective projection. So we've got slide happening here. Let's save the rotations for a while. Instead go into matrices and see, can we do something more interesting here? So I'm going to make another operation here called set perspective. And instead of just taking left, right, bottom, top, near, far, self perspective will take a field of view, or a field of view y, we can call it as well, because it's a field of view in the y dimension, an aspect ratio and then near and far. So now we can use these to set self dot near equals near is fairly simple. Self dot far equals far. Self dot top equals near times the tangent of the field of view divided by 2. Self dot bottom equals minus top. Self dot right equals top times the aspect ratio. So that's how much wider it is than its high. Self dot left equals minus right. So now I've set new values for these. This, however, is not entirely enough because I can't use these near, far, bottom, right, left, far values in the exact same way as I do an orthographic projection. So instead we're going to have to go here and set up a new matrix. So this matrix, you can actually use this here, except first differences are there are values here. You put B and D here. And the bottom line is 0, 0, minus 1, 0, instead of 0, 0, 0, 1, because this is a nonlinear transformation that gives us the perspective transformation. However, we can't use the same values for A, B, C, and D. Does anyone have the slides for those, or remember them? Yeah, if you can just read them up, actually.
A is equals to 2 divided by self dot right minus self dot left.
Okay, so that's 2 divided by self dot right minus, that's the width, self dot left. Like so. Oh, yeah, okay. Yeah. It's 2 times near, 2 times, well, self dot near. This is in the slides anyway. 2 times self dot near divided by the width. Let's just make sure everything is set up nicely. C is basically the scaling factor for the y dimension, so that's 2 times self dot near divided by self dot top minus bottom. Okay, the translation factors here are, it was, yeah, right plus left divided by right minus left. Negative. Self dot right. Sorry?
I don't think it's negative in the slides.
No, probably not. So it's just self dot right plus self dot left divided by, let's just try it the way it's in the slides. I think that's divided by self dot right minus self dot left, the width. Okay. Then we'll have D here, which is the same except for top and bottom. Top, bottom, top, bottom. So we've gone through how, thank you, how all of this kind of works in the lecture. So I'm just going to write this up here rather than we used E and F, right? E equals negative F minus N, which is self dot far minus self dot near divided by, no, it's far plus near divided by far minus near. Could have just copied that the way it was though. Like so, far minus near. So F, we have the same division, but it's minus 2 times far times near, right? Like so.
But the E, at least I have done it near minus far, the latter part.
Did you do it near minus far?
Yeah, near minus
Which
far.
is the same as minus far.
No, the like what you divided with.
Oh, it's near minus far. But do you still have the negative on the...
I'm not sure. Did I do it wrong way?
Because as soon as you switch one of them, you can just skip a sign somewhere else and it doesn't matter if it's near minus far or far minus near, if you just skip the minus in some other place. Let's see how this... Yeah, exactly. Put what in parentheses? This one. This is the only one that's not in parentheses now. It doesn't really matter. It's all multiplication and then there's one division, so it shouldn't really matter. Well, either way. So now that we're... Okay, set perspective needs one more thing, which is self is orthographic equals false. So as soon as we set orthographic, orthographic becomes true, and that means when we get the matrix, it goes into the correct way of fetching it. This should work now. I'll just leave this here so people watching the video can pause and just read it off the screen. And make sure that this is in here in the set perspective operation. Okay, so now we would like to go into the main program, and instead of setting orthographic here, I'm simply going to comment that out. I'm going to do self.projection matrix dot set perspective. Okay, so our camera, 90-degree camera. It's a pretty wide camera, especially because it's going to be wider on the sides than it's up and down. But okay, pi half. Again, make sure that you know whether you're using radians or degrees and be consistent in using them. I'm just using radians throughout, so I actually have to send pi divided by 2 in there. If you want to use degrees, if you feel something like 90 degrees here is better, you have to very much make sure that when you are setting the perspective, you don't just do field of view divided by 2, you have to do field of view times 180, no, times pi divided by 180 here. Just make sure you understand the difference and that you're doing everything consistently according to the way you want it to be. All right, so this is 90 degrees. The aspect ratio, 800 divided by 600. You can just write that, or you can calculate it beforehand and send in a number. Near, let's just have it 0.5 again and 10. So we have the same near plane and far plane. Now, if we did everything correctly, we should have the camera in the same location, looking at the same stuff. Nope, it crashed. Top is not defined. I forgot a self, I guess. Minus self dot top. Minus self dot top minus self dot right. Okay, so again, I can move to the sides, I can see these things, but more is changing than just kind of a two-dimensional image going from left to right. And if I go backwards, I actually feel like I'm getting distant. Again, it starts far plane clipping there. We can move the far plane further away, great. It starts near plane clipping if I go too close. But it feels like I'm going closer and further away. It doesn't only start clipping. There it starts clipping. It also does other things. At this point, it'd be cool to see if we can experiment with z-buffer fighting. And actually go ahead here and see what happens if I say, okay, I just want the near plane to be insanely close. And I just want the far plane to be really far away so that no near plane or far plane clipping happens to me. I'm going to see if it actually, maybe the computer is just, okay. absolutely nothing. That's a little bit more extreme than what I was hoping for. Let's try smaller or less extreme numbers. Is it affecting the calculations more than I thought it would? Okay, this is z-buffer fighting. It can't decide up here whether it should draw the face on the back or the face on the front. Both of them are being rendered. They have different normals, so they get different lighting calculations, but it can't decide. You see these? It's rendering what's on this side instead, because it just gets the same values for the pseudo depth. The same depth value goes into the pixel, and it just can't decide which one should be drawn. And so we get classic z-buffer fighting. And this is simply because we're taking the most, or basically the best resolution in pseudo depth values, which are closest to the near plane, and we're taking like probably more than 9/10 of our pseudo depth values, and we're packing them somewhere into nothing before we even start drawing stuff. So now let's put the near plane like fairly far away, but still closer than the objects that we're drawing. Let's just have a sensible far plane. 100 is okay. As far as we're using the resolution close to the near plane, we're good. So no z-buffer fighting, and I could move super far away before it starts far plane clipping. Oh yeah. But if I go really close to here, I'm going to get some near plane clipping. But near plane clipping we can just control by deciding how close can the camera actually move. Like, where does my collision stop it? And when I feel nice with that, then I just put the near plane as close to that as I can. So I have no clipping, but also no problems with how close I can go. So that's our perspective. Let's do one thing. My time's almost up here, but let's try one thing here. Take the buttons T and G, I think. T, G, call it T key down, G key down. There. That means I need buttons for it. Here, T and G. And then let's take this. All right. So what I'm going to do, ViewMatrix, is I'm going to make a variable that we can just call, let's call it field of view. Self.fieldofview minus equals, I don't know, 0.1 times delta time. I think that'll be too small a change. Let's make it a little bit more. 0.25. So A is, no, that's T. We want T to actually make it smaller. We want G to make it bigger. Let's see if this does something for us. Now we need to actually define that. So we're going to do self.fieldofview up here where we set up our projection matrix. I'm going to do self.fieldofview equals pi divided by 2, which is a nice start. Then I'm going to take this stuff here, like I took from the view matrix. I can leave it here, but I'm also going to copy it and I'm going to put it in the display function. If I'm going to change the values of this frame by frame, if I want an animation, I have to set these in the shader for every frame in the display function, not just in the initialization function. So here we have stuff we did with where's the stuff we did with the ViewMatrix? That's here. So we just do the projection matrix here as well. And instead of doing pi divided by 2, we're going to do self dot field of view. Let's see if this does something. Okay, so now I'm moving backwards. Now I'm zooming in. The difference is that, well, it's just very different. I can, for instance, walk closer and zoom out at the same time, and we're just changing the perspective. We're just getting a lot of perspective distortion around there. So zoom in, move away and zoom in at the same time, move towards it and zoom out at the same time. It's a cool effect. So one is zooming, and as soon as we start rotating the camera as well, it's gonna really make a difference whether we have a super long lens or not. So I'm just going to see what's left of this lab exercise here. So we went through it. We set the view matrix as an identity matrix. We set up the look for the view matrix. We set up slide for the view matrix. We haven't done roll, pitch, and yaw yet. We set some keys. You can experiment with that more. So yeah, these are just experimentations. The lens of the camera, we set the field of view aspect near and far. We changed GetMatrix so that it works as well. We set up the zoom so we can play around with that a little bit. So should we set up one version of a rotation just to make sure that it works? We'll go a little bit overboard with the time. Let's go, just to have a template for the other rotations, let's go into, no, not base 3D objects, matrices. We're going to go into the view matrix. We have look and slide. Which rotation would be most interesting to add? Looking up and down, looking to the sides, or rolling the camera? Roll. All right, define roll. Self. What do we need to send in there? Just the angle. Okay, so what is this going to look like? Start with C equals cosine of the angle. S equals the sine of the angle. Oh. Okay, so what does the slide say we want to do? We want to rotate basically the, we want to rotate the u and v vectors around the n vector. Temp vector will be, temp u will be the vector u times, yes, self.u times the cosine plus the vector v times the sine. Then we can say v equals almost the same, except we're going to have it times minus the sine here, and times the cosine here. And then we say self.u equals temp u. Okay. Thank you. And we'll see if this, so hopefully this should just work. Go into the program. Let's just change what we're doing on these keys. So A and D, let's change that from sliding to the sides to rolling. That would be self.ViewMatrix.roll. We have this angle variable that's always changing over time, so let's just use that. Self.angle No. We can't do that. Want a specific change here. So we want to roll, let's say just pi per second. Pi times delta time. Like so. There. So which one should be negative and which one positive? We'll just find that out. Then it'll be the wrong directions now. So the camera is rolling in the correct directions actually. So D is positive in my case. No. D is negative. Right is negative. Doesn't matter. So the camera is rolling. I can roll, I can move backwards at the same time. Roll, move forwards. Roll and zoom. So much more fun when we can actually start walking around and turning and all that, and then we can see what effect the zoom has, see what effect the getting closer and further away has, roll and all that. Now we've basically incorporated all of these things. We haven't finished this entire lab exercise because what it does is just more or less more of the same. So roll we have, pitch and yaw is just the same except the other vectors. Then we have to start thinking about things like if we need to be stuck to the floor, if we look up, we don't want to move up. We want to be looking up, but we still want to be moving forward. If we look up and then look to the side, we don't want to kind of go tilting off axis like this. Instead, we want to be looking at the same angle up while we go around. So we have to change. We have to make alternate versions of these if we want to be walking like in a first-person view. We want to be able to not just yaw, but instead to kind of look around us in a way that's sensible. And we don't want to slide always in the direction that the camera is pointing. We want to slide along the floor. So we have to work on these a little bit, experiment with them. But that's a very good kind of base to our next assignment, is just making sure that the camera is moving in a way that feels correct when we're in this space. So I can actually look just a little bit at, I'm going to do one thing here. I'm going to open no, it isn't here.
Can you show that roll one again? Roll function.
Yeah, the function roll. Yeah, sorry. Matrices roll here. So what I can do, I can go into the, where am I at? Here, here. Here, I'm just gonna make sure I'm, sorry to the ones watching the video that you're watching a blank screen at this point. No, that's not it. This is it. Here. And this one, yes. So I can just open another code window here. So we have two code windows now. So I'm just going to run this one. See if this works. Just to kind of show how we can set up something from exactly the same code, except where we can move closer and further away. We can look to the sides. We can roll. It's hard to, so let's roll the camera in the other direction. We can move, well, I didn't have anything at this point to move directly up and down. We can roll around. In this case, when we're moving around, if we go ahead and just steal a little bit from the other code, here, I'm going to steal this and put it here, there, there. I'm going to steal from the top here as well. Oh, it's so slow. Here, T and G. Up top here. Add T and G. So I'm going to add the zoom here as well, just the same way as we did it in here. Okay. Then I need to add the variable, field of view variable. Wow, this is so... I'm in here, yeah. Where did we have the field of view variable? It's here. Let's just steal this entire part here. Stick it up top here instead of the projection stuff. And finally, the part where we actually set it in the display function. Jumping past this all the time. Yes, set projection. Just go to the display function here as well. Before we set the ViewMatrix. Okay, let's see if I could steal all that code and just make it work. You can kind of see a little bit. If I go closer and I look around, you can see how this feels, looking around here. If I, however, instead zoom in and then look around, it's kind of entirely different. It's like I'm really far away. It's just exactly like having a zoom lens. You know, when you look around, it doesn't feel like you're up close there, kind of looking inside the scene. It feels like you're really far away, just looking past it. Now here, when we're looking around, it feels like we're inside the scene. It feels like we're close to these things, looking around right next to them, like so. If I instead zoom in, then looking around just kind of moves them out of the way. So we have all these different controls: zooming out, zooming in, moving. Sorry, couldn't find that again. And the fun zooming out while moving closer. Perspective effect. All right, so any questions regarding this? I think at this point we've kind of gone through this. Like I was saying before.
Really negative.
Sorry, is what really negative?
Really negative.
Ah. On the roll in update, we have if the D key is down, then we're going negative pi times delta time. If the A key is down, we're going positive. So is something flipped in your code?
Yeah, for some reason it goes the other way.
Maybe it's not because that is wrong or the roll is wrong. Maybe the entire thing is flipped. I mean, maybe somewhere else in your matrices there is the x coordinates are flipped, or left and right is flipped somewhere. That's possible as well. Just in your perspective projection, that left and right for whatever reason are flipped, and then your entire it can be many reasons. But if it's consistent and you feel correct with it, and you can build on top of it, then it doesn't matter if it's flipped or not. I mean, it's all relative to the consistent way that you handle your coordinate frames. So you can flip your entire scene and it'll just look the same if you just are consistent in flipping everything. So yeah, I don't think there's anything in particular here except just more of the same. Make the yaw and slide ones as well. Looking at this, the lens, we have that. And then the most important part, just experiment, experiment, experiment. Have fun with this, start doing the assignment, start building things, start moving the camera around, and just get a feel for working with 3D. So thank you very much for your time. I hope all of this will be helpful to have like in a compiled video to be able to at least check if something is really weird in your program, that I did it the same way or possibly differently.